Okay, I think we're ready to jump into the main keynote presentation, a little bit ahead of schedule. So I'm going to introduce the speaker. I think we all know him. He's very distinguished. It's Dr. Bob Gilbert. He is the department chair in the Department of Civil, the Maseeh Department of Civil, Architectural, and Environmental Engineering. And he's going to be giving a presentation on the work he did along with Dr. Carrasquillo on the failure analysis of the Arecibo Observatory Telescope collapse in Puerto Rico. So, Dr. Gilbert.
Thank you, Ryan. Thank you, David, for all you did for our students, for our department, for the university, and for our profession. It's an honor to be here. There are a lot of my colleagues here, and it's a lot easier to give a talk when you're in front of a bunch of people you don't know than it is when you're in front of a bunch of people you know. So I will do my best. I'm going to talk about the failure of the Arecibo radio telescope. It's based on a project that I was a part of that produced a National Academy's report explaining what happened and what we can learn from it. And the committee was made up of these individuals, and the one I want to highlight is Ramon. So Ramon Carrasquillo was a part of this committee. Ramon was from Puerto Rico. Ramon was very excited to get the panel to Puerto Rico and take him to his favorite restaurants and show him around. And unfortunately, Ramon passed away before the report was produced. And Ramon was just a great person. He had a wonderful heart. And I'm going to tell a Ramon story that has to do with my wife, Lizanne. My wife was building a tunnel in Dallas under the Trinity River right next to IH-35 when it comes into downtown. And the river flooded in the middle of them building this tunnel, and the tunnel collapsed. And the entire downtown Dallas was in jeopardy of flooding because the tunnel went under the levee. So if the water got into the tunnel and up the other side, it would have flooded downtown Dallas. And Lizanne called me and said, I'm trying to figure out how to design this plug, and we need concrete that's really strong and that cures really fast and that doesn't shrink, and I don't know what to do. And I said, call Ramon. So she called Ramon, and Ramon immediately helped her and not only figured out a specification, but also figured out somebody in the Dallas area who was qualified and able to produce that concrete very quickly and get that plug going. And then as they were starting to work on the plug, the whole tunnel collapsed and a sinkhole went all the way up to the surface right next to IH-35 on a Sunday afternoon. And Lizanne said, we need help, and called Ramon on a Sunday afternoon. And Ramon got his whole network in Dallas to help. And concrete truck after concrete truck went to the site and filled up the sinkhole all the way up to the ground surface. They finished it at 6 in the morning on Sunday before rush hour traffic went over IH-35, and no one knew anything had happened. But that was Ramon. Ramon would just do whatever he needed to do to help, and I miss him. Okay, we are going to go to Arecibo in Puerto Rico. It's about 40 miles west of San Juan, and it's the home of a radio telescope. The radio telescope had a large dish, which is about 1,000 feet across. It had a platform that hung 450 feet over that dish and weighed about 900 tons. That platform was both a transmitter, so it would send radio waves out, and it was also a receiver, and the dish was used both to transmit those radio waves and also to receive and focus those radio waves. For a sense of scale, it's a really big structure. It's also a movie star.
No wonder we couldn't see it.
ready to signal the satellite.
How do you stop it?
The transmitter above the internet.
That gives you a good sense of scale. There's some special effects there, but the telescope itself, that's real. That's how big it is. It was built in 1963. It was built in order to detect intercontinental ballistic missiles coming in. It was given over by the military to the National Science Foundation in the late 1960s and turned into a scientific observatory. It was upgraded in 1974. They put in a new surface on the dish and put in a new transmitter on the platform. It's probably most famous because it sent out what's known as the Arecibo message in 1974, which Carl Sagan was a part of. That was a message to the universe saying, we're here, we're intelligent, we have this big radio telescope. They even sent a picture of the telescope to explain how they were sending the message. And of course, they sent a Beatles song. In 1997, it was upgraded again. And it has all sorts of accomplishments over its history, including the first evidence of neutron stars, and the list goes on and on. So it was a very valuable piece of equipment for the scientific community. In the early 2000s, the government stopped funding it as much. The National Science Foundation really wanted to move on. The scientific community fought back, and really over most of the 2000s up through 2015, there were people trying to get rid of the facility and people trying to hang on to the facility, and finally in 2016, they made a decision to keep going with it, and the University of Central Florida took over operation of it from Cornell University, which had been both the designer of the telescope, but also the operator of that facility all the way through 2015. And then in 2020, it passed away. I'm going to show you a video. This has no special effects. This is not from Hollywood. This is real. Had a big life and a big death. So what happened and why did it happen? That's what this panel that was put together by the National Academies was charged with. We're not the only ones. Lots of people have looked at this. NASA did a lot of work on it, looking at the materials and what caused this to happen. WJE was a part of it. Thornton Tomasetti was a part of it. And then our particular panel put together a report that came out in 2024. So what I'm going to tell you is really a synthesis of all this work. The beauty of our report is that we were the last ones, so we got to use all the information that had been produced. So the structure itself. The original structure had a platform that was suspended over the dish by a set of cables, and there were 3 towers. And on each tower, there was 4 cables that came to the tower from the platform. And then there was a set of cables, 5 cables on the backside of each tower that were backstays and anchored in the ground. So that was the original structure. In 1997, when they upgraded it, they added quite a bit of weight to the platform. And so they added additional cables called auxiliary cables. The original cables are now called the main cables, and the new cables called the auxiliary cables. And those auxiliary cables consisted of 2 cables per tower that came off of the platform, and they're shown by the red lines in this diagram. The cables themselves are made up of a bunch of wires that are grouped together, anywhere from like 160 to 230 wires in each one of those cables. They end at sockets, which are steel sockets that have the wires terminating in them and are filled with zinc in order to create the connection. So here's what that socket looks like in terms of how it's fabricated. The cable is inserted into the socket. The wires are pulled away from the cable, which is called brooming. Molten zinc is then poured into the socket, and as it solidifies, they then stretch the cable and kind of lock that geometry in. And so now the zinc is really, for the geotechnical engineers in the room, acting in bearing on the front of the socket. And we always like bearing capacity better than we like shear. They have a number of configurations in terms of the termination of the socket, but they're all basically the same. And here's just an example of some of those sockets terminating at one of the towers. In the very foreground, you can see one of the auxiliary cables coming in. There's one of those on either side. You can see the 4 main cables coming in from the platform. And then on the back side, you can see the 5 backstay cables that go down to the ground where they're anchored in. The failure itself started in August of 2020. On August 10th of 2020 at 2:35 in the morning, one of the auxiliary cables broke, the one at Tower 4 specifically. And when it broke, it pulled right out of the socket. And because the platform is not symmetrically held up by those auxiliary cables, the platform swung and rotated and was damaged. Here's a picture of it after that happened. So there's Tower 4 where the cable broke from. Here's the platform, which is now damaged because when the cable broke, it swung and rotated and moved in a way it wasn't designed for. And that cable weighed about 2 tons, so that cable smashed into the dish and damaged the dish. They started looking at it, trying to figure out what are we going to do, what do we need to do. They put together a plan to replace the auxiliary cables. On November 7th of 2020, they were going to get started, but they never got to get started because on November 6th of 2020 at night, at 8:15 at night, one of the main cables at Tower 4 broke. And this one, again, pulled out of its socket. So here's the back side of those 4 main cables coming in from the platform, and the one on the left you can see is no longer there. And at that point, they decided, well, we need to take this thing down. We're not going to be able to save it, so they started developing a plan for taking it down. But before they could finish developing the plan for taking it down, at 7 in the morning on December 1st, the remaining cables at Tower 4 that held up the platform all broke. They knew Tower 4's cables were in peril, which is why the drone was sitting there watching Tower 4. In fact, there were workers the day before that were climbing around on the telescope, trying to figure out the plan for how they were going to decommission the telescope. Here's what happened in that video. The first thing that happens is a wire breaks on the second of the main cables coming into Tower 4. and then about 3 seconds later, that cable gives way, and shortly thereafter, each of the next 2 cables gives way. Once all those cables are gone, it's now pulling on that one last auxiliary cable that was left, and that's the last thing that you see snap as the drone starts to look toward the center of the platform. I'm going to show you that video one more time now that you know what you're looking at. So why did this happen? The sockets all failed, and it was pretty clear that they were pulling out from the core. So when you looked at the ends of the cable, you could see the part of the cable that used to be in the socket with the zinc around it, and it just pulled, sheared straight out of the socket assembly. The disconcerting thing about these failures was the first failure had a load on it that was less than half of the nominal capacity of that cable. And we typically don't talk about the capacity of the connections of the sockets themselves. We talk about the capacity of the cable, and the factors of safety are on the capacity of the cable, and we just make sure that the sockets are at least as strong as the cable. And in fact, when they produce the sockets, they pull on it with a load to make sure that it's the cable that's going to go and not the socket that is going to go. The second failure again happened with only 62% of the nominal capacity on that particular cable. And I think the important thing I want to point out here is as they were working on figuring out what to do and how they were going to do it, they kept calculating factors of safety, assuming that the cables all had their nominal capacity when they already knew that one of them in August had failed with much less than its nominal capacity. A number of different mechanisms were considered for why this happened. I think everybody immediately thought it had to do with corrosion because we're here in Puerto Rico with a very corrosive environment. The zinc could have corroded, the steel wire could have corroded, the steel socket casting could have corroded. There were a lot of things that could have corroded. They had various measures in place to try to minimize the potential for corrosion, and in looking at everything, there was no evidence at all that corrosion had anything to do with what happened. Stress cracking and hydrogen embrittlement were also high on the list of what might have happened here, but again, there was no evidence of that. Fatigue of the steel wires right where they were connected to the socket was another possible mechanism, but again, there was no evidence that that's what happened, and it came down to the zinc spelter was creeping. So here's some of the forensic evidence from the first socket that failed. This is from the NASA report. You can see that the wires have broken in tension, and they basically snapped like they were fresh wires that were pulled to their tensile capacity. There was no evidence at all of fatigue, and the wires that were tested all had the same strength that they were supposed to have. When they looked at the zinc, there was evidence of creep, not just creep, but secondary and tertiary stages of creep. I'm not an expert in mineral, I can't even say it, but I don't know what I'm looking at in this figure, but the people at NASA that do this for a living were very convinced that creep of the zinc is what happened. And as a reminder, secondary creep means that the strain rate is a constant with time, and tertiary means it starts accelerating and then goes to failure. Now, creep in zinc is generally something associated with very high temperatures, not with the atmospheric conditions that were in play over the life of the Arecibo telescope. The other interesting thing about creep is that the wire that first broke, the cable that first broke, was not one of the old cables that had been there for 57 years. It was one of the new auxiliary cables or younger auxiliary cables. What exactly was happening in terms of the mechanism is shown with this schematic. So when you cast the zinc in there and then you pull on it, the zinc goes into shear, and as it goes into shear, the wires that are in the broom start to pick up that in tension, and you come to an equilibrium point, and the zinc actually goes into compression. It arches right at the base of that socket, which is where it gets that bearing capacity from. And the idea is that this happens when you first pull on it, and then it sits there at equilibrium like that forever. But what happened in these particular sockets was that as it pulled on it, and as the zinc was in shear at equilibrium, instead of it staying there, it started to flow. And as it started to flow, that meant that the socket started to move, and that meant that the wire tension started to go up, and eventually the wires broke, and then the socket was now just held in place by shear in the zinc, and it couldn't hold that load anymore. Here's some evidence of that zinc creep. The sockets you would expect when you put that seeding load or that initial load on them would move about 1/2 of an inch. That's what almost all of the sockets here at Arecibo looked like. So here's an example in 2003 of a picture of one of those sockets. You could tell whether things were moving or not because they were painted from time to time, and if the paint was no longer continuous, you could tell that the socket was moving. There was no evidence of that for all of the sockets, including this one between 2003 and inspections all the way through 2011. However, after Hurricane Maria, which was in 2017, they noticed that several of the sockets had much bigger pullouts. So here's the socket that failed in 2020, a picture of it in 2019, where instead of 1/2 an inch, it's now over an inch of pullout. And you can also see the paint. You can see how that part was never painted because that used to be inside that socket and it's no longer inside that socket. Now the loads in Maria were not significant. The biggest increase for any one of the cables in this whole system was 15% over the sustained gravity load. This cable, M4N, which is the one that broke, was loaded negligibly in Maria because of its location relative to the wind field. In fact, it might have been that the tension went down a little bit in Maria, not that it increased in Maria. And yet that's where we see the evidence of the slip. There were a number of sockets with pullout. So here's just looking at the auxiliary sockets. Again, the younger sockets. Every one in red is basically where the pullout is more than what you would expect. And you'll notice that on the towers, and every one of the towers where the cables were coming into the platform, there was evidence of significant pullout. On the backstays, there was evidence of pullout. One of the interesting things about this schematic is that none of the connections with the platform itself exhibited pullout. The conclusions, and I was happy at this point as an engineer because I figured, okay, like these sockets broke, they broke unexpectedly, but as engineers, we're always thinking about making sure that things like this, if they were to happen, aren't going to take the system down. So the conclusions are all related to that. Number one, providing redundancy is important. The auxiliary cable system, where there was a single cable along each one of the load paths, did not have redundancy. What that meant was when one of the cables broke, the system distributed loads in an uncontrolled manner, and that caused damage to the platform. It also meant that if you were going to replace one of those cables, it was very difficult to replace one of those cables in service. The second lesson is that the connection should not be the controlling design element. This is the one thing that our panel differed with Thornton Tomasetti about. Thornton Tomasetti said we should increase factors of safety on these socket connections. Well, you don't really apply a factor of safety to a socket connection. You apply the factor of safety to the cable itself. If you increase the factors of safety, you're going to make the system heavier, and that means now you need even bigger cables. And there was no evidence about what factor of safety would have been enough so that this didn't happen. This is unprecedented. There have been 100 years of experiences with these zinc spelter sockets, and no one had ever seen something like this happen. Carl Frank met with our panel. David Goodyear met with our panel. They both worked on this telescope in 1981 when they replaced one of the damaged cables. They were dumbfounded about why this would happen and how this would happen and how this wasn't consistent with all the experience they had with these sockets working just fine. So I hope if you take nothing else from this, if you're in some committee meeting and someone is saying, well, Thornton Tomasetti said for cable-stay bridges we should increase factors of safety because of what happened at Arecibo, say, no, that's not right. That's not going to help us, and that's not a valid conclusion to draw from what happened at Arecibo. The third lesson is that you really need to keep track of what's going on, and it's best if the designer at the beginning figure out what's important, what to be looking for, how much socket pullout is okay and how much is not okay, how many wire breaks are okay and how many wire breaks are not okay, so that the people inspecting it have a guide as to what they're looking for, and the people operating it have a guide as to what to do when they see something like 1.5 inches in one case of socket pullout. The fourth lesson is that actions need to be taken quickly when an element needs repair or replacement. So they knew that there were some damaged cables after Hurricane Maria. They had a plan to replace those. As of August of 2020, which is about 3 years after Maria, they still hadn't done that. When the first cable broke, they started planning and figuring out, what do we do now and how do we do this, and doing a bunch of calculations and looking at what the loads on the other cables were. And while they were doing all that, the next cable broke. And then they started planning for decommissioning, and while they were putting together plans for decommissioning, the whole thing just fell down. So you really need to act quickly. You need to be ready when something goes wrong to act. And then the last lesson is that the safety of the workers, both the scientists, but then after that first cable broke, the engineers that were trying to figure out what to do, and the public. So you see where that cable from Tower 4 broke and smashed down into the dish. If that had been on Tower 12, which is the tower that's in the foreground, that's where the visitor center is. That's where the public would go to look at this telescope. If that cable happened to have broken when there were people on that platform and it broke on that tower, that potentially would have put those people in peril. And yet, in all the decisions that were being debated about whether to keep this telescope going or not, they even did an environmental impact statement where public health and safety was one of the factors that they considered. In that analysis, they never talked about the possibility that the structure itself was in peril. The only thing they looked at in terms of health and safety was that this telescope potentially could detect asteroids that were coming at the Earth, and therefore it was going to protect the general public. So they were worried about an asteroid hitting the Earth. They were not worried about somebody climbing around on this structure. The one thing that I'll point out is every one of those cables broke in a non-working hour time. So we are very lucky. The day before that cable broke that let the whole thing come crashing down, there were people on that structure. I do a lot of work with the offshore oil and gas industry, and we have analogous structures. Everybody that was working on this telescope talked about how unusual this was, that you had these cables under sustained tension, and maybe that was the problem. Maybe we shouldn't be putting cables under sustained tension. Well, we have a lot of experience in the offshore putting cables under sustained tension. For example, the spar structure, which is out in the Gulf of Mexico. Again, a very large structure like Arecibo. Again, the mooring system is a set of cables that are connected to the platform and connected to anchors at the seafloor. Again, those cables are under sustained tension under normal service conditions, and then they go into increased tension potentially under extreme loading conditions. And some of the lessons, we've been operating those floating production systems offshore for about 25 years at this point. The first is that these lines do fail. The failure frequency for the offshore lines is about 2.5 times 10 to the minus 3 per cable per year, which is consistent with Arecibo. If you took that rate and you applied it to the cables that were there for 57 years and then the cables that were there for 23 years, and you figured out how many cables you would have expected to have broken in the lifetime of that facility, it would have been 4.5. And in fact, 4 of the cables at one time or another had broken during the lifetime of that facility. So that experience is very consistent. The majority of the offshore failures, like at Arecibo, are at connections. The offshore failures are nearly always caused by a reduction in capacity at the connection rather than an overload, which is exactly what happened at Arecibo. We've concluded that larger factors of safety in offshore design wouldn't prevent the failures because they're not failing because of overloads. They're failing because things get damaged during installation or things are deteriorating, generally because of corrosion or hydrogen embrittlement. So that's also similar to what happened at Arecibo. However, we have never had experience with creep like this in one of those connections. 2 things are not like Arecibo. One is these offshore systems are designed for at least one line to be missing. So we just assume at least one of the lines is not going to be there, and the system should be just fine under that condition, and it takes more than 2 lines generally for one of these systems to fail. And the second thing is that with these offshore systems, we expect we're going to be replacing lines. There are projects I've worked on where part of the capital budget was extra lines and the storage of those lines and the contingency for how they were going to transport those lines and install those lines when they needed to. So from day one of that facility, they were expecting that they were going to be replacing lines periodically. At Arecibo, they didn't really know what to do, and they knew they needed to replace some lines, and they were scratching their heads trying to figure out how to make that happen. The one question, though, that is troubling is why zinc creep? Again, we've got about a century of experience with these kinds of sockets, and never, to our knowledge, and there are people on my panel who have connections, no pun intended, and a lot more experience with these types of sockets and have never seen something like this happen. We have a hypothesis that it might have something to do with what's called electroplasticity. So what this is if you stick a current through a metal like zinc, the flow stress, the stress at which it starts to flow, is reduced. And the bigger the current density, the bigger the reduction in that flow stress. This was discovered in 1963 with zinc in exactly the same year that Arecibo was constructed. And the Arecibo telescope was the most powerful radio transmitter on Earth. So this platform was transmitting an enormous amount of electromagnetic energy, and potentially there were currents running in these cables, and those currents had to go somewhere. The question is, can low levels of current, orders of magnitude smaller than the current densities that I'm showing on that plot, cause long-term electroplasticity? We don't know. But there's some circumstantial evidence. First of all, if you look at wire breaks, wires were breaking pretty regularly at first. And then when they installed the first upgrade in 1974, the wire breaks started to reduce in frequency. And when they upgraded it even further in 1997, the wire breaks really reduced in frequency. So one possible hypothesis for why that was happening is if the bigger electrical currents were allowing the zinc to flow, then that was reducing the stresses on the wires and they weren't breaking as much. The second piece of circumstantial evidence is where the cables were that had the most pull out at the sockets, and particularly where the ones that failed were. They were at the tower. So the same exact sockets were at the platform end of every one of those cables, but there was never any evidence of just pull out at those cable ends, and nor is that where the weak link was in this system when it ultimately came down. It was always at an end far away from that platform, which also potentially makes sense in terms of that transmitter and how those electromagnetic waves are getting pushed out from that platform. It might affect those tower connections more than what's right next to the platform itself. Again, it's a hypothesis. We don't have any measurements of what the currents were in these cables. The other thing to note, though, is where the pullout was where cables were terminated in a certain way. So it was specifically where cables were terminated in a way that the only way, if there was an electrical current in it, it could pass would be to go through the zinc in the socket. So some of the cables had grounds naturally in the way that they were connected so that there was another pathway. Some of them had multiple pathways where a current could have gone. But the auxiliary cables in particular were the ones that were the most susceptible potentially to this kind of a phenomenon because they weren't grounded in any way. So if the current was going through that cable and it got to that socket end, the only way it could go was to go through the socket itself. That report came out about a half a year ago now, and since that time, we've gotten some more information. Because of that report, someone sent us a picture of cables from Arecibo indicating that they were arcing. So this would indicate that there possibly was current running through these cables. The second thing is Habib Tabatabai at the University of Wisconsin-Milwaukee, who was a member of my panel and who refused to stop where I wanted to stop, which was, let's just be engineers. We know things can fail. Let's design systems so that if they fail, it's not catastrophic. He would not let go of why this was happening with these zinc spelter sockets. And to his credit, he kept pushing and pushing. And there were members of our panel like John Sully, who's an expert in this, who didn't want to have anything to do with electroplasticity, didn't believe it had anything to do with what was going on, kept saying, no, don't put that in a report. Eventually got convinced by Habib that, okay, we can stick it in as a hypothesis, but let's not make that the main point. But Habib just kept pushing and pushing and pushing. And after the report came out, he started running some tests at the University of Wisconsin-Milwaukee where he put pure zinc wires in tension at about the same level of tension as they would have been in a relative sense at Arecibo, and then passed a small current density through them, orders of magnitude smaller than what I showed you on that plot with the evidence of electroplasticity in zinc, and he found that they were moving. He's only run tests that have gone out like 7 days so far. He's setting it up again, and he's going to run something longer. But so far, the evidence is that at very low levels of current, the zinc is flowing. So in summary, I think it's a pretty simple case history in that we should always be expecting the unexpected. We should have a plan in place for when it happens, and we should act quickly to mitigate it when the unexpected happens. With that, I would like to thank David again for your service, and I would like to acknowledge Ramon Carrasquillo. Ramon, I miss you. Thank you very much. And I'm happy to answer questions, but I don't know if we have time.
Absolutely, yes, plenty of time. Yeah. Any questions for Dr. Gilbert?
Feel free to raise your hands, or if we have any questions online.
Joe? Questions? Sharon?
Thank you, Bob. Hey, you mentioned that these types of connections were used a lot in bridges. But you haven't, I mean, okay, maybe you don't have the electromagnetic currents or something, but is there really no evidence of this type of creep in the bridges that Carl and David were talking about?
Not that we are aware of, no. I do think this idea of us being careful in where currents are going that may be inadvertent is probably a useful message from this. Some of the people we talked to who do have a lot of experience with bridges said they would periodically getting shocked by the cables on the bridges when they were inspecting them. So there was current that was being generated in some way that was inadvertent. So, you know, designing it such that there's a ground and that you have that current going where you want it to go might be a good idea if you're using these types of sockets.
Yeah, I mean, what was amazing to me is how many measurements had been taken over the life of this telescope, which you would not see in most cases. Or it was an unusual structure, so there was so much, you had a lot of forensic data to go back and look at.
Yes. And it was run by a bunch of scientists, so yes. But they didn't, even though I think most people who look at those pictures of the sockets that had pulled out an inch or an inch and a half, you know, unexpectedly had concern. Like, that's not what's supposed to happen. Something's going wrong at that point. You may not know what's going wrong, but something is clearly going wrong, and those need to be addressed quickly. But they didn't address them quickly. There's a question back there.
Is it common in some of those other applications for them to have eccentricity in how they're anchoring? Because, I mean, looking at that, it almost seems like them being offset from the central axis. You're getting, potentially with wind, different stress profiles in those versus the ones that are dead center in line with the telescope platform.
Yeah, I don't know. I don't think that was something that was of significance in this particular case. That angle that I drew is probably more pronounced than what it really was, and it's a pinned connection. So yeah, and in the offshore, yeah, we sometimes during different loading conditions will have them loaded off the line that they're intended to be loaded on. So I mean, it's something that if it were significant, I think would be potentially of concern, but I don't think here. Yes?
Your number 2 summary is have a plan in place for when the unexpected happens. And yet, to Sharon's point, they were taking measurements throughout the life of the telescope. What were they planning to do with those measurements? It seems like they'd have an idea, a reason to take the measurements. What were they going to be doing with them if the information, as we found out when they had the jump from a half an inch to an inch and a half or inch and an eighth, where was the plan? They had to have, didn't they? It seems to be a very interesting curiosity to me that they take measurements for measurement's sake, but not to have a plan to why?
Yeah.
Can you speak on that?
So when the University of Central Florida took over, we interviewed the person that was the principal investigator for the project that was the University of Central Florida taking over operation of the telescope. And he was irate about some of the conversations he had had with the engineers where he would ask, well, how much pullout is too much pullout? And how many wire breaks are too many wire breaks? Like, is it 5? Is it 10? What is that number? And he never got a good answer. So I can say there wasn't a plan. Can I explain why there wasn't a plan? No. But I think it's a good lesson that you should have a plan, and you should know that when it's 5 wire breaks, that's when you need to start to think about replacing it, and you need to do it quickly. You can't wait years and years and years when you know something needs to be replaced. Yes?
Dr. Gilbert, I think we have a question.
I don't have the number, but it's much lower than modulus of elasticity of steel. Does it play any role? I have never seen, I've seen post-tensioning where you actually use wedges versus pouring zinc. Would that have any role in this?
I think it's an intentional, so it's how that socket works as a system, because the zinc flows and that pulls that socket together and into tension, and you get that arching of the zinc right at the head of the socket. So it's how it's supposed to work, and then you get the wires going into tension and the brooming because of the relative stiffness of the zinc compared to the wires. But, you know, did it have an influence here? Yeah, because those wires were in tension, and when the zinc started flowing more, the wires got into so much tension that they broke. But again, the people I worked with on this, no one is aware of this happening anywhere except at this particular telescope. So I don't want you leaving here worried about zinc spelter sockets. Worry about zinc spelter sockets when you're using them on a telescope like Arecibo, where you've got this huge electromagnetic field that you're operating within.
This is a question from online. What improvements to the connections could be implemented to reduce creep or reduce shear in the wires?
Yeah, I think if the hypothesis is correct that it was due to electroplasticity, the solution would be to ground the cables so that there's an intentional pathway for electrical current to flow so that you don't have the current flowing through the zinc in the socket. Anybody in here have experience with creep in one of these zinc spelter sockets? I think we're good then. Okay. Thank you all very much.
Okay, really quickly at this time, I'm going to offer an opportunity to anybody in here who would like to come up and give any remarks about their experience or story with Dr. Fowler in their past, either through career, through school, a funny story perhaps. Does anybody have anything they want to share at this time? Okay. Stuart? Yeah, there we go.
I would just like to say that this is very special for me because I did my graduate work at UT, and my two primary advisors, Dr. Yersa was my primary advisor, Dr. Fowler was my secondary advisor here. Dr. Harville-Wheat was involved in my research as well, which was related to corrosion. And so to see those faces in this room is very special to me, and it's, when I think about it, the reason that I'm here, like physically here in Texas, at UT, is because of the people in this room. And as a matter of fact, he probably doesn't remember it, I'm sure he doesn't, but I got a call from Dr. Yura when I was in an undergraduate, and it was just, kind of a, hey, we would like you to come down to Austin. And that meant a lot to me to get those kind of calls and those kind of contacts. And then I'm sure she doesn't remember it also, but I remember when I was in graduate school, Dr. Wood, I had her concrete course, and I think I probably procrastinated on an assignment and did kind of an all-nighter thing and turned it in. I turned it in on time, but I was kind of haggard and a little bit rushed. And I think she saw that, and I remember I think I turned it in at the lab. I just remember being at Ferguson, and she pulled me into her office, and she just had a completely normal conversation, not about concrete or about the project, just kind of a, how are you doing? Maybe she was checking in on me. I might have looked a little worse for the wear, but I really appreciated the kind of community that that this place fosters. This is a very special place, and so I'd like to thank each and every one of you affiliated with UT for being here, and especially those that I mentioned. So thank you.
Thank you, Stuart. I guess I have one funny story from Dr. Fowler that still gets talked about today. In the last time he taught the forensic engineering course at UT, one of my friends was in the class, and part of the class is giving a group presentation at the end of the semester, and Dr. Fowler is sneaky. He's notorious for appearing to be asleep, but we all know that he is very aware of what's going on at all times. And through the slip of the tongue, my friend referred to something in the presentation as masonry, and Dr. Fowler, who appeared to be sleeping in the back row, quickly pointed out that it is, in fact, masonry, and asked if he got his education at A&M. So that one still gets told many times over today, and so we enjoyed those kind of stories. So if anybody, anytime throughout the day, wants to tell anything to the group, feel free to come to us during the breaks or at lunch, and we'll get you up here to tell a story. And at this time, I think we're going to try to get a group photo with everybody in the background with Dr. Fowler.